Hello, it's Keith here, and this is lesson 1 of the Hello World series of my 65816 assembly programming tutorials, and we're looking at the Super Nintendo today. We're going to create this Hello World message, the one you can see just here, and we're going to do this on the Super Nintendo. We've got a self-contained example, that's the point of the Hello World series, that will show this, and we're compiling with the WLADX assembler today, which is a 65816 assembler, because yes, I've done Hello World and Super Nintendo before, but I always use 6502 mode because I'm more of a 6502 programmer. So today we're going to use the 65816. The reason we're doing this is for my new book, which by the time you see this will be out. My second book covers 5 new assembly languages, including 65816, ARM Thumb, 6809, PDP 11, and RISC-V. So hopefully you can buy that on Amazon now. There should be a link in the description and the comments below. So please check out that if you want to support my content. Anyway, today we're going to see the example. The example's in the book, but you can also download it from the website as well. You can get it for free, so you don't need to buy my book. You don't need to do that at all. So let's go to the source code and let's see how we've built today's example. Over we go. Okay, so here is the hello file. You see the hello world.asm here. And we're going to compile this with the WLADX assembler. Now, the WLADX is a bit of a pain for me. The way it works with regards to setting up the output is a bit more difficult than I would like. So basically, I'm used to very simple assemblers that just create a big and nice binary file. WLADX is designed for more complex memory mapping and for multiple banks and things, and it does all of that automatically for you. The problem is if you don't want to do that automatically for you, you kind of have to give it some defaults, and that is what we've got here. So we've got these basic definitions here, and really all this is doing is telling it to create one dumb file and with no splitting or anything, but you have to define that. So you have to define that slot 0 starts at memory address 0 and that it's a size of 20,000 here, and you have to define that there is a total of 1 bank and that the first bank has a memory size of 20,000. You have to do that. If you don't do that, nothing will come out. And we also have to tell it that we're going to start bank 0 slot 0. So as I say, really all of that was just what we have to tell it to get it to output anything, and then we're starting at memory address 8000 with our cartridge here, and we're going to start our program here. Now we do have some 0-page entries we're defining with symbols here. We're defining these as a pair, well, as a triplet actually. This is a 24-bit triple. So the low part is the ZL, the high part is H, and the third part, the upper part, the third byte of the 24-byte triple, is the HOU part here, and these are mimicking the EZ80 register names. I tend to use Z80 type conventions just to attempt to keep my sanity supporting so many different systems, to be honest. So the HOU is the highest byte of the 3, then the H part is the high part of the 16-bit part, if you will, and the L part is the low part, and HL can be used to specify all 3 if we wish. Now my prog is the start of our program, but if we go down to the bottom of our code, you will see that we're actually jumping to reset vector 8000 at the start of our code here. So this is where our program resets to, and that will start our program up. Now, what do we do when our program starts? Well, the first thing we're doing is we are turning on 65816 native mode, and we have to do that via the carry. So first we're disabling interrupts here, we don't need them. We are then clearing the carry, and we're transferring the carry to the emulation bit here. So we're turning off emulation effectively here, and that is enabling 16-bit mode, and that allows us to do new things. Now what we're doing next is we're basically setting up the processor settings. Now the processor settings are split into 2 parts. There's the XY register pair, they can be 8 or 16-bit, and then there's the accumulator and memory, they can be 8 or 16-bit. And what we're doing here is we're setting the indexes, the X and Y, to 16-bit, but we're keeping the accumulator as 8-bit. So our accumulator and our memory functions are still 8-bit. So that's what we're doing there. Now we can change these at any time. We need to tell the processor with that rep command, the reset processor settings, and then we need to tell the assembler with that index option there, that index compiler assembler directive there is telling the assembler to start outputting 16-bit XY commands, but still 8-bit accumulator commands. Now what we've got next is a series of writes, and these are some values that we need to write to the hardware to set up our screen. We're not going to go into these in detail. Basically we just need to send the write commands to the video hardware to set the screen up in the way that we want. what we need to do next is we need to set up some colors. Now our example is actually using color 3 for our font, so we need to set up color 0, the background, and color 3. The way we select a color is we write the color number to register 2121, a memory map register, and then we send 2 bytes to 2122. Now these will be the blue, green and red bits. Here you can see those bits in that format there. Now the first color we're setting is color 0, so we write the color 0 to 2121, and then we set the palette entries, and all of those are 0 as well, to 2122. Next we set color 3, and we're basically setting this to yellow, and so that is the correct bits for the color yellow. If you want a different color, you can change those. Okay. What we're going to do now is we're going to set up our font. Now we've defined a bitmap font in our code, and as I say, this is designed to be typed in from a book, so we've got a very limited font here. Basically this is 1 bit per pixel, so we've effectively just defined a single bit plane, 8 bytes for a single line of our font, and we've just got a space and A to Z, no numbers, no symbols, because as I say, it's intended that you could type this in. Now, when we define our bitmap data within the hardware, it's a little bit of a pain. Now, the first thing we do is we select our VRAM destination with port 2116 here. We're writing to VRAM destination 1000, and then we need to send our color data. But we send it in 2 parts. Basically, we send 2 bit planes, bit plane 0 and 1 first, and we send all 8 bytes for those 2 bit planes, and then we set bit planes 2 and 3, and we send the 2 bytes for those separately. Now I suspect the reason that you do that is to maintain compatibility with the NES. Now you see the Super Nintendo in its early development was going to be backwards compatible with the NES. That got abandoned, but I think some of that compatibility hung along, and I think that's why we're kind of defining 2 bit planes first and then the other 2 bit planes second. I think that was part of that intended backward compatibility. Now what we're doing here is we're loading in a byte from our font, and we're writing that to the first 2 bit planes here, and that is why we're selecting color 3, because either those will be both 0, which will select color 0, or both 1, which will select color 3. And so we're sending those bytes first. The first 8 bytes are our font data. The second 8 bytes are all 0, so we're not selecting anything else. If we'd written other values to there, we would end up with a color potentially above 4 all the way up to 15. So we're writing those to 0, and we're repeating until we've done our entire font there. Okay, so that's set up our font in the tile pattern data. Now we've got some more stuff to do with our screen. We're setting the default scroll position here. That's setting the screen position, and we are selecting our tile map here. We're clearing the tile map here. We're selecting the memory address 0, and then we are writing all of the tiles within the tile map to 0. That is basically clearing the screen. Memory address 0 is the start of our tile map definition, and each tile entry is 2 bytes, and we'll see that a bit later when we start setting characters, because when we show a character to the screen, what we're actually doing is we're setting a tile of the visible screen to the pattern that we've defined within our font. Okay. Well, our screen is now basically ready, so the last thing we're doing is we're turning on the screen. We're turning on layer 1 here of our screen, and that is the one we're going to use for our tile map, and then we're turning on the screen here. So the screen is now enabled. Now we have a cursor X and a cursor Y entry within our 0 page. These are the next character that we want to show to the screen as we print our font to the screen, our text to the screen. We're going to do it character by character, and so X and Y are tracking those positions, and we're starting them at 0 here. What we're then doing is we're loading the 24-bit address of the hello world string into L, H, and HLU, HLU being the top byte of the 24-bit triple, H being the middle byte, and L being the low byte here. So that's that there, and we're calculating the top byte there by basically shifting it 16 bits to the right, so taking only the top byte of the 24-bit address there. Now our hello world message is here, and you'll see that it's a combination of upper and lower case. But when we run it, of course, because we haven't defined any lowercase, we're going to have to fix that. So we're going to have to convert that to lowercase, as you can see here. And it's our print string routine or our print char routine which is going to do that. Now our print string routine, if I can find it here, here it is. Our print string routine is basically going to read in bytes from that 24-bit address. You can see we're using square brackets here around HL. That specifies that it's a 24-bit address. And so we're loading in address bytes from the HL 24-bit triple there. And we're waiting until we get a 255. Our string is 255 terminated, and when we get one, we're going to give up. Otherwise, we're going to print the character to the screen. Okay, well, let's take a look at that print char routine. Here it is. Now the first thing we're doing here is we are basically clearing one of the bits of our ASCII character, and the reason for that is that by doing this, by clearing that bit there, we're effectively converting this to uppercase. And then what we're doing next is we're seeing if we've ended up effectively at character 0, and if we have, then we've been asked to print a space, and in that case we're going to skip the next line and we'll just jump down to here. The next line is effectively subtracting 64. The reason we're subtracting 64 is that that is effectively the ASCII character A, and so we're basically jumping and correcting for A. Now if we tried to print characters to the screen other than ASCII, other than letters, numbers, or greater than, less than symbols, things like that, they would show as other data. They would either appear as blank or garbled or the wrong character. As I say, this very simple version is only designed to print A to Z in the character space. Okay. So the first thing we're doing here is we're backing up the HL pair. We're going to use that HL pair, only the low 2 bytes of it, for calculating our VRAM address. Now our VRAM address, we're going to basically calculate the tile memory address within VRAM. Now what we're basically going to do is we're going to calculate the memory address, and what we need to do is we need to take the Y position, which is the cursor Y, and we need to effectively multiply it by 32 because there's 32 tiles across in our tile map as we've defined it. So we're basically bit shifting the Y part into the correct position here. What we're then doing is we're adding the X part, the X position of our character, and that will be the horizontal position in tiles. Now that has now selected the correct VRAM destination. We've got that in the HL pair here, and then what we need to do next is we need to wait for VBlank. We can't write to VRAM outside of VBlank, so we've got to wait for VBlank routine here. We're basically reading in from port 4212, and we're waiting until that top bit becomes a 1. That will tell us that we're in VBlank. Once we're in VBlank, what we're going to basically do is we are going to load in the 16-bit value from the HL pair here, and we're going to store that 16-bit value because remember the X register is in 16-bit mode here. We're storing that to port 2116 and 2117 as well, but implicitly because we're writing a 16-bit value there. And this has now selected our VRAM destination here. Now, what do we actually want to write to our VRAM destination? Well, we need to write 2 bytes, and these are basically the tile number and the tile pattern number and also some other possible information. Now, for such a small entry, we actually only need to use 1 byte because our font is so tiny. We're using very low pattern numbers. If we were using a pattern number over 256, we would need to write a 1 or something here, but because we are not, we just write a 0 to 2119. We then write to 2118, the tile number. We've pulled it off the stack here. We pushed it onto the stack all the way up here. This push of X is being matched by a pull of X, and that's basically to restore the HL part of our HL triple there. Now we've now shown our character to the screen. Writing that pattern number to the screen will effectively show it. So all we need to do now is increase our cursor X, moving across the screen 1 tile, so that next time we draw a character to the screen, it will appear in the following place. And that's how we are able to show our hello world to the screen. Just 1 character at a time along the screen like that. Okay, so that's our file, but how do we actually assemble it? Well, I have a batch file that I use, but you could do these from the command line if you wanted to make things slow for yourself, I guess. But basically all we need to do is we need to do 2 stages to assemble our program. The first one I'm doing is I'm using WLADX65816exe, and this is compiling into an object file, and then I'm using WLALink to build this into a final file. So we need to specify our source file, which is, because I'm using a batch file, this %1 here. We need to specify an output file with -o, and that is this object file here, which is the intermediary stage. I'm also defining a symbol here, build SNES. Now you wouldn't need to do that if you don't want, but I define a symbol marking the output system, and that's how I do my multi-platform code. Now this -I switch here, this is for the listing file. Basically it outputs some included information which we can then build into a listing file here. So I'm outputting that as cart.txt. Now a listing file is basically just debug information. Now the final thing we've got here is that we are specifying to output a binary file, and the destination is cart.sfc here. Now, the way I'm running that is I'm doing it from the command line here. We're running SNES here. You can also use SNES 9X if you prefer. And then we just specify the cartridge file, and that will run the program straight away, which is very quick and saves us a lot of time. And there we go. So that is the end of today's example. As I say, if you're interested in 65816, if you want to support this content, you want to see more 65816 specific stuff, please consider buying my book, because as few people buy the book, I will make more content. So anyway, I hope you've enjoyed this. Go to the website, download the source code, the build scripts. I've got a whole set of 65816 tutorials already on my website and YouTube channel, so you don't need to buy my book. You can just go and watch those as well if you just need more content. Anyway, hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.